let me preface today that what we are doing right now isn't really the goal. I'm just trying to train you. And you guys who have had a course in physics understand that you're not going to do any of this stuff. But there is stuff we will be doing that you need this stuff in order to proceed. This is just the getting you trained, learning some vocabulary, and being able to, the nice way to say it is being able to attach what you might witness with what you're seeing here. Remember yesterday you walked in, or last week, you walked in front of the motion sensors. The idea there was to understand the connection between your motion and what the graphs might look like representing your motion. Now we're focusing on the graphs, hoping you can use your imagination to kind of interpret what it is you're seeing here with the graphs. I want to make the connections back and forth, which is what I intend to do today and continue tomorrow. But you need to progress too. So, is there anything from the worksheet, except for the last one, are there any of these, or even earlier, that you would like me to discuss or go over? Because if you don't, then my assumption is that you are proficient. And I could test that proficiency tomorrow. Tomorrow's not a surprise, I've been talking about it all week. I will be testing your proficiency tomorrow, first 15 minutes of class. You will be asked to replicate one of these. Probably answer some questions related to them too, that I'm sure will involve all of the things we discussed yesterday, average velocity, average speed, displacement, all that stuff, plus what I'm going to add to it today. So, are there any of these to which you would like me to speak and maybe review? Natalie, right?
Number 2.
On which page?
On the creating a position graph.
This one?
Yes.
So what I'm going to do is, I've got it all marked off here, so this is the answer. But I'm going to erase all that so we can have a fresh look at it, okay? And the first thing I want to remind you about is that I have limited capabilities when it comes to producing graphs and publishing them for you guys to be able to work. So this package doesn't mark 0. You should mark 0. I will remind you of that tomorrow. All right, so this is get nice and big. There. What I see here is a velocity versus time graph. And before I even go into reviewing it, let's think back to last week when you just walked in front of the motion sensor. When I look at this and try and interpret what I see here, it looks like the object is moving at 5 meters per second, right at the start. So it's moving away from the origin at 5 meters per second. And then abruptly, after 4 seconds, looks like it's going to walk at -1 meter per second. Well, that's back from where it came, but it's walking slower. And then it speeds up a little bit, but still in the same direction, going -3 meters per second. Without any hint of what the actual graph looks like, away, slower, faster. Right? You should be able to do that with what we did last week. You maybe not, but that's a quick expectation of what I think the graph might look like. Now that's not going to get you any credit tomorrow, but a quick little sketch on the side might let you know, oh, whoa, I'm making a big mistake somewhere. Now, I'm saying that because when I look at these pictures, I see there's clearly a section of the graph here where this area is going to be positive. Then an abrupt change, creating this section right here, where this area is going to be negative, but clearly smaller. And then another abrupt change, and this area right here where I have a really small area. We all in agreement that those are kind of the three sections? Now, in order to transition to the position graph, one of the things that you need to start recognizing is that the position graph is telling us about the same event. So I have 10 seconds of evidence on my velocity graph. I need 10 seconds of evidence on my position graph. They capture the same event. Now, to help you, I would also mark things that look important. Something abruptly happens at 4 seconds. I'm going to mark 4 seconds as an important place on my graph. And something abruptly happens at 9 seconds. I'm going to mark 9 seconds as an important place on my graph. Something must happen there. Now, labels are important. When it comes to grading and receiving full credit, labels are important. You neglect things like this at your own peril. So, I think it's time we can move forward now. Kind of figure out what happened. This is where I will physically look at the areas by calculating the area of each section. So this first area has a base of 4 and a height of 5 meters per second. So 5 meters per second times 4 seconds is 20 meters. It's positive. Keep that in mind now. I don't need to use it right away. I'm just going to keep it in mind. Now I've got this other area that ends here and is this wide. It looks to be 5 seconds wide and negative 1 meter per second tall. That looks to me to be negative 5 meters. And then I have my last little area here, negative 3 meters tall and 1 second wide. Am I good at just writing negative 3 meters and be done with it? We good? These represent the total displacement, total distance traveled, all sorts of things. If I was just answering questions, I'd say the object traveled 28 meters, but is, 12 meters away from where it started? You follow me? Now to actually graph it, I needed more than one area before I start graphing, and the reason is to set the scale. You have to set a scale on your position graph, and you have to try and utilize as much of the position graph as you possibly can. In order to do that, you need to understand where your limits are. So knowing that it moved 20 meters in the first section, well, I don't know, is that the farthest it goes away from the origin, or is it going to go farther away from the origin? That's why kind of estimating what's happening in your head ahead of time is a good idea. They move forwards, and then for the rest of the time, move backwards. This helps you establish your scale. So I now know that it never goes any further than the 20 meter mark here. So I'm going to use that as my scale. Scale means even increments in all directions. It's a number line, remember. So now I believe we can get to the point of graphing. We are told in the instructions to start at the origin. I'm starting at the origin. In 4 seconds, we traveled forwards 20 meters. I'm going to identify the 20 meter mark and the 4 second mark. Now, here's where people make mistakes. The next displacement is negative 5. That doesn't mean I go down to negative 5. This is a displacement. It's a change in position, but I've already moved 20 meters forwards. So this is 5 meters from here back towards the origin. So I start here and move backwards 5 meters. And that's going to be the 15 meter mark, which I'm going to make it right there at 9 seconds. And now from here, I go backwards another 3 meters. Now, we have to connect these dots. And yesterday we kind of blew through that, but we need to be very aware of this portion, especially as we venture past this. The velocity was the same the whole time over the first 4 seconds. That means that the slope of the line I'm about to draw has to be a slope of 5 for the whole interval of the first 4 seconds. That means a straight line. For you, that means a ruled line. If you want to ensure that the person grading your test, me, or your neighbor, can adequately say that this is a straight line, it must be ruled tomorrow. Everybody understands? We don't give the graders any reason to not believe you. So straight edges is a good idea tomorrow. You're allowed a straight edge on the exam. We have one. Now, I'm going to connect all these with straight lines because I am familiar with this one in that all of the velocities are constant within their intervals. This does create discontinuities in my graph, but there were discontinuities in the velocity graph. So we've reached the end. We've done all the things we were supposed to do for this graph. Does that adequately demonstrate what you need to be able to do? Is that adequate, or do you need more practice? Or do you have other questions? I am happy to do both. Yes, ma'am.
So like for the first one, this cubic, it like the zero, like crosses, like the line that crosses like the big box. So that would just be the area.
So you're talking about the first example?
Yeah, like we wouldn't use that bottom part.
Well, we know that for the first 2 seconds it's not moving, so yeah, it just stays there. Is that what you mean, this part right here?
Yeah, like we wouldn't use that as an area.
Right, no, it's got an area of 0. Yeah, because its height is 0. All right. If there's no other questions, then we need to really transition to what our goals are for today. And I don't mean for today. Our goal is actually to handle this example. And this example is the reason we're studying this. Everything else before this is arbitrary. This is what happens in nature. We look close to this, we realize that there aren't any of these flat bar things anymore. That's very artificial. Things transition in a natural way. They speed up, they slow down. This is what this is showing us. You should endeavor, take a few moments, to come to grips with what this graph is actually displaying. Remember, it is a velocity versus time graph. In your mind, describe what's happening here. Think about it. I'd go second by second and kind of help identify what you think the object is doing. Here are some important questions to ask yourself, especially if you are new to this. What direction is the object going at time equals 0? How fast is it going? Does that change between time equals 0 and time equals 2? Is it getting faster? Is it getting slower? Is it still traveling in the same direction, or is it traveling in a different direction? Be able to describe that. Is there any place in the graph that seems interesting, or something appears to happen? Be able to describe that. I'll give you a minute to kind of review it in your mind a minute, and then we're going to talk it out. By the way, everything we've talked about as of yesterday applies to this graph. There's areas here. There's places where you can compute the area based on the shape. When I look at this graph, I notice that the object starts at 50 meters per second. That's pretty fast. It's positive. So it's moving in the positive direction, 50 meters per second. After 2 seconds, it's going 30 meters per second. That's slower than 50. But it's still positive, so it's still traveling away from the origin, but not quite as fast. And I will notice that it got there under a smooth transition from 50 to 30. No discontinuity in that graph. After another 2 seconds, it's now at 10 meters per second, still smoothly transitioning from 30 meters per second to 10 meters per second. When suddenly it crosses the origin, it stopped here. But didn't stay stopped. It just stopped and then started to speed up again. Now it's going 10 meters per second. So it went from 0 meters per second to 10 meters per second. It's getting faster. But these velocities are negative. After a couple more seconds, it's getting faster still, but still moving in the negative direction. And finally, it's back to the same speed it started at, but in the opposite direction. If I was to sum that up in a single sentence, this object traveled away from me while slowing down, and then stopped, turned around, and came back towards me while speeding up. That's what must have happened. Everything I just said supports that. But moreover, it seems to me that there's an area here. I hope you see it. I see an area here. Remember, area is defined as the curve bound by the 0 axis. We don't go all down here. It's bound by the curve and the 0 axis. Now that's not a rectangle, but that's okay. All of you suffered and survived middle school. So it's a triangle, right? 1/2 base times height. I have a height right here. I have a base right here. Seems to me 1/2 base times height. Right, my height is here, 50. My base is here, 5. 1/2 base times height. Half of 50 is 25, and 5 times 25 is 125. So this is positive 125 meters. Start to put that on my position graph, but I don't know what the range of this is going to be, so I probably should look at least one more area. So I'm going to look at the next area. These are all things you should have been able to do yesterday. Unless you really want to tell me you couldn't figure out the area of a triangle, and I don't think there's anybody in here who wants to admit that. But I'm thinking, here's some areas. Right there. That looks like another triangle. Basis goes from 5 to 10. That's 5 again. And it goes to negative 50. So 1/2, 5 times negative 50, or negative 125 meters. Well, if I was just talking about yesterday, so far this object moved a total of 250 meters. Distance traveled. 250 meters. 125 meters away, 125 meters back towards. But its displacement 0. So it came back to where it started. So let's have a look-see. Position. Meters. 10 seconds of time. 10. And that's time. Something special happened at the 5-second mark. It was stopped, so I'm going to mark the 5-second mark. Seems like an appropriate place to mark on my graph. I don't see anything else I can feature. Told in the instructions to start at the origin, starting at the origin. After the first 5 seconds, there is a positive displacement of 125 meters. After that, it's a negative displacement. So I'm going to set my scale all the way to the top, 125. All the way to the bottom, negative 125. I've set my scale. I could put markers in there, like every 25 or something. I'm not going to right now. But I am going to say, all right, at 5 seconds, I was 125 meters away. Now, from here, I have to figure out where I am after the next 5 seconds, and I'm supposed to go backwards 125 meters. So, looks like my next dot's going to be down there at the origin again. Now would be a good time to say, Mr. Sheldon, I don't know where you did that, or I don't know how you got that. So we're good?
Did you get that?
What's that?
How did you get that?
I have 2 displacements. So after the first displacement, you got that so far, right? Start at the origin, move forward 125 meters. I start from here and then apply this change of position, which takes me backwards 125 meters.
Oh, so you went backwards, okay.
No worries. I find it always best to make sure that we get our questions answered now so we're on rock solid ground. I don't always reply great to questions, but I'll try. Now, you might be compelled to connect these the way you connected things before, but when you connected them before, we knew our velocity was the same all the time. And we know the slope of whatever I draw in here has to reflect the velocity. Was the velocity the same all the time? So my slope here can't be the same all the time. In fact, my velocity was never the same number twice. So my slope here can never be the same number twice. So let's take a look. We can estimate it. At 0, what was my slope supposed to be? 50. The velocity was 50, so my slope at the start has to be very steep, because it has to be a slope of positive 50. So I'm just going to draw in like a little piece of slope. Something to clue me in that I have a steep slope there. I'm going to advance to each of the points and see if I can get another bit of information. For example, at 5 seconds, my velocity was 0. Well, that means at 5 seconds, my slope has to be 0. 0 is flat. Put a little piece of slope in there. It's a clue, a guide. And then at 10 seconds, I'm noticing my velocity is negative 50. Well, that's a slope that's got to be the same as the other one, but negative, not positive. So I'm thinking something like this. A piece of slope to kind of give me a clue. Now, when I look at that, there's no way to connect these with straight lines. I'm going to have to draw a curved line. And I'm not going to try and hazard a guess as to what this curve is. There's ways to prove what this curve is, and you probably have some ideas of what this curve is, but for the time being, I just want a nice, smooth line to kind of bring this all together. Mediocre curve line. I probably could do better if I cared more, but I care. But I'm just not going to do it again. This is good. Good for me. You should do better. You're the one being graded tomorrow. There are features here, like the fact that it's concave down. That's important. The fact that I have a clear place where the slope is 0. That's important. Symmetry on both sides. That's important. But more important, does it say to me what I think it should say? The object left, reached some maximum height and came back, or reached some maximum displacement and came back. If I pick points along it, does it show me that the velocity is becoming a smaller number? There are slopes here. Slopes at a point are tangent to the slope, to the point. Seems to me like those tangents are becoming smaller. Their slopes are becoming smaller. The idea of the tangent here is something you should already know, but if you don't, I'll reinforce it. The slope at a point would be the same as a tangent line at that point. You learned tangents in geometry. Or you didn't. But you were supposed to. You kids hate it when teachers say that stuff, but we love to say it. Somehow it makes us feel superior. It shouldn't, because they're all the stuff we forgot too. We do the same thing year after year. I had a feeling I was about to be interrupted. I knew I needed a bit of a break before I said something important. This is not easy the first time, but there are things about this that I really want to go over. And I think we've kind of hit the big stuff here. But I've set something up purposefully so we can kind of take a look at this. We've done stuff like this before. So what I would like to do is consider, well, where this really comes from. So this isn't arbitrary. As I said from the very beginning, this is kind of, natural. It's what's really happening in nature. So I've got a bit of an experiment set up here. I've got the motion sensor here, and it is currently set up for a 5-second experiment. The cart is in front of it, so it should be able to be picked up by the motion sensor. And I set it for 20 samples per second. So I've not run the experiment yet, so there's going to be a bit of a delay, and hopefully when I'm done, it'll put what we need to see on the screen. So let's get ready. I need to be outside of the range of the probe, 20 centimeters or so. All right, so I want to call your attention to this because I think it's very clear and emblematic of what we just saw, right? Do you see the things I'm seeing? There's the part where I threw the car, right? It wasn't really moving and suddenly it is. That's me throwing the car. So I did that, but then afterwards it's on its own. Do you see the velocity appears to have a nice, consistent slope to it? Yeah, there's little bumps in here and there because the track has little bumps in it and stuff. But it looks pretty consistent. I'm noticing that the slope is negative. Are you noticing the slope is negative? Just like our example, right? I'm noticing a curve here, just like our curve. It has all the same features. So this must be position. It shows me that the cart reached some point far away from where it started. And that point corresponds with where it stopped. Do you see all those same things too? Now, I want to be very, very careful here. This is kind of an organic picture of what we saw, what we see, a simple experiment. I pushed something up a ramp, it left me, slowed down because it's on a ramp, came to a stop, and then returned back towards me. Clearly that's what we have as our picture. Now our picture has the object going at 50 meters per second. Had I done that, the cart would be in the lunch lane somewhere. And I didn't want to do that, so this one was slower. But it's still pretty demonstrative of what we saw, right? And so would you agree that our curve for position seems, at least in some way, very much realistically portrayed here? Now, there are things about this that are going to be troubling. So let's maybe talk a little bit about the troubling parts. We didn't talk about this yesterday, we just brought it up. But the area stuff, that's pretty easy. We never talked about the slope, except to say that the slope had units we had never seen before. We should come back to that today. Because I think the slope is telling us something. If you'll recall, you're supposed to evaluate every graph for slope and area. And yesterday, the slope was meters per second per second. Now, just a brief bit of, let's just say, this is trivia that I think you should know. Anytime you measure something and it has units of seconds in the denominator, it is a rate. Meaning, it is telling you how fast something changes. That's what an interest rate does, right? Tells you how much money they're going to charge you every year, month, day, hour. Rates. Rates tell you how fast something changes. So although you could say this is meters per second squared, for the first couple of weeks, I'm going to say meters per second to help us acclimate to the idea that this slope is the rate of how the speed changes. How long it takes to go faster, or how long it takes to go slower. I mean, technically what I would say is that this is the rate at which the velocity changes. And that is the technical definition of acceleration. Acceleration is a tough word, and it's a tougher concept. I say that not because it's hard, but because we have so many misconceptions built up around this word. First, acceleration does not mean to go faster, even though the word decelerate means to go slower. I will never use the word decelerate in class, ever. It's misleading. Now, I want you to look at our example from just a moment ago. The slope here is negative the whole time. Right? Clearly negative the whole time. But was the cart slowing down the whole time? It slowed down on the way up, sure. But didn't it speed up on the way down? But you do notice that the slope was always negative. In fact, do you also notice that the slope was negative at 0? You're going to get this question wrong in the test. I'm going to tell you that right now, and I don't know who you are. I won't exploit you. Is the cart accelerating when it stopped? I know, it's confusing, and I see people shaking their head because your knee-jerk reaction is to say, of course not. But is there a slope here? Remember how much I pointed that out yesterday? Is there a slope right here? Yeah. Which means it must be accelerating when it stopped. It had to. You want to say it's not, but it has to. There was the acceleration used to stop it, but then there's the acceleration used to start it back up again. If there was no acceleration when it was stopped, it would have just stopped on the track and not moved again. But it was accelerating the whole time. So when it made it to that point where it stopped, it was still accelerating. That's what got it started again. It's not like it stopped for a long period of time, did it? It instantaneously stopped and started moving again in the other direction. The big banner thing here is the entire time the slope was negative. But that doesn't tell you whether it was speeding up or slowing down. That's an implication. Knowing if the slope is negative or positive, knowing if the acceleration is negative or positive, does not tell you if it's speeding up or slowing down. You think it does right now. In the same way that you think to accelerate means to go faster. Wrong on both accounts. If we look closely here, this slope, let's do it real quick. Rise is negative 50. Run is 5. Negative 50 divided by 5 is negative 10 meters per second per second. So the acceleration pictured in this graph was negative 10 meters per second per second. For the first 5 seconds, it was slowing down. Right? Started at 50, was reduced to 0. That's this point to this point. For the next 5 seconds, it was speeding up, just in the negative direction, starting at 0 and going to 50. If the acceleration is in the direction of motion, your object is speeding up. If the acceleration is in the opposite direction of the direction of motion, then your object is slowing down. If the acceleration is in the direction of motion, you're speeding up. If the acceleration opposes the direction of motion, you're slowing down. Speeding up and slowing down requires that you know the acceleration and the velocity. You need both. One will not do. A negative acceleration does not mean automatically that you're slowing down. Now, That's a lot to take in for a few minutes, but I want you to consider that I'm expecting you to be able to utilize this information to maybe take a velocity graph like this and make a position graph. This object, from just looking at it, I know because I have information about velocity and time, I can tell you this object is speeding up. Positive slope, positive initial velocity. However, if you wanted to find the displacement, you do realize that that's not a triangle, right? Now, you have methods of finding areas of shapes that you might not know. Like you might break it up into a rectangle and a triangle. But it's a trapezoid. You know the equation of a trapezoid, right? I'm sure you do. I'm sure you remember that it's 1/2 times the sum of the bases times the height. I'm sure you remember that. You would never want to admit to Mr. Shelton that you didn't remember something that you were taught years ago. That it's 1/2 times the sum of the bases. The bases are these parts of the trapezoid. Base 1 plus base 2, and it is incredibly essential that you learn this by tomorrow, or at least learn it tomorrow. Times the height, which is this part. Don't break it up into a rectangle and triangle. I want this. But if you do break it up into a rectangle and triangle, you can prove that this is the formula for a trapezoid. Because you're smart people, you can do things like that. Maybe. I don't know. Maybe you can. I don't know. I would hope that you can. Try this, please. I know the bell rings for lunch here very, very shortly, and I will not keep you from lunch, but try this right now. I think we can do this. We have 3 minutes. This object velocity starts at 2 meters per second, ends at 10 meters per second. The time interval is 5 seconds. To me, that suggests that there's a displacement of 1/2, 2 plus 10 times 5. 2 plus 10, that's 12. Half of 12 is 6. 6 times 5 is 30 meters. I can construct a position graph, understanding that my entire interval is 5 seconds. And the motion goes from the origin to 30 meters. I can construct a graph. I have 2 points now. Now, to connect those, not a straight line, but I will notice that at time 0, the slope is 2. That seems shallow to me. Not quite 0, though. Partial slope. Not quite 0. Slope of 2. But at the end, slope of 10. That's bigger. Slope of 10. Since it's not constant, smooth curve to connect them since there's no discontinuities. Concave up. Important. Do I have a graph here that shows that the velocity is always increasing? Yes. Was this object getting faster or slower? You should be able to tell me. Was this acceleration positive or negative? You should be able to tell me. I suspect you guys can find the acceleration because you can find slope. Right? Rise is 10 minus 2. The run is 5. Rise over run. So, let's see, that's 8 over 5 or 1.6 meters per second per second. The bell rings now, or at least the chime's going to go off. So I think this is a good place to end.